features. So, thank you. Thank you. It missed my great introduction there. All right, so we're talking about correlations and doing algebra. So each dot here is a person, and that person might have some feature down here given by this value and a different feature measured here. This might be, I don't know, their height and their weight or something. And you see they're correlated. So if the person's taller, then they're more likely heavier. And these are the sort of correlations that machine learning looks for and is all based on. So let's start by understanding these correlations. And to make it concrete, let's do a dating service. All right. So you have all these clients, and each client has various features. And for every pair of clients, here's a pair of clients, we're going to compare them, see how well they're compatible with each other. So we can look at, for example, they both like movies a lot. They both have a big positive number. We're going to multiply those numbers to give you an even bigger number. And that will be the contribution to how compatible they are. Compared to nature, neither of them care much about nature, neutral about nature. And so when you take the product, it doesn't contribute that much. One is very introverted and one's very extroverted, right? We have a positive and negative number. So they multiply to give you a big negative number. And so that detracts from their compatibility. While here, neither of them like animals, and you take the product of two negative numbers, you get a big positive number. And so you multiply each of those and add them up. And in this case, you get a big negative number, which means these people aren't correlated very well, right? But if you take this pair of people, you do the same, you multiply pairs and add up, and you get a positive number, 900, right, as opposed to negative 800. So these people are more compatible, right? And we're going to think of, for each person, we have a tuple of numbers. And whenever you have a tuple of numbers, we call it a vector. And when we compare them, their compatibility, it's called the dot product, is you sum over all coordinates of the product of the value of the one vector times the value of the other vector, and you add it all up. All right. So let's go. Vectors can be thought of as directions and distances. So let's do a little bit of algebra from high school. You might remember this relationship between the lengths of triangles and this angle here. And so then if we think of these as vectors with various lengths, the same thing applies. And you can calculate a length of a vector by doing Pythagoras theorem. And so then you rearrange this equation, and what you get is that the correlation between these two vectors, which is the dot product, it relates to the cosine of the angle here, for whatever that's worth. All right, and how do we use that? Is, well, one way to compare two vectors is the projection. All right, we fix the green W edge and shine a light down, and the size of the projection is the size of the shadow down here. And what we see is if the two vectors are correlated well, they get a big positive dot product, which gives you a big positive projection. On the other hand, if they're not correlated well, then you get a negative dot product and you get a negative correlation, right? You see how in the first case, the two vectors were sort of moving towards each other, less than 90 degrees between each other. And here, the angle between them is bigger than 90 degrees, right? So what about this vector here? It's at 90 degrees. And so the projection, the size of the shadow is 0. and the dot product is 0. And if you took all the vectors, all the x vectors that are perpendicular to this, here's one vector, you take all vectors that are perpendicular to it, you're going to get the definition of this plane that's perpendicular to that green arrow, right? And why is that cool is because if you want to know which side of this plane you're on, are you a blue dot or are you a red dot? What you do is you take the dot product of the dot with the green W vector, and if it's positive, you're on one side of the plane, and if it's negative, you're on the other side of the plane, right? So we're going to use that for separating. It's called linearly separator, is if you can draw a line and separate the red dots from the blue dots, that's separatable. But right here, it's not so clear you can separate them with a line, right? So if you were here last time, we talked about these artificial neurons, and they have an X value. The input is this tuple of numbers, and each of the numbers gets fed into one of these little nodes here, and each edge has a weight. So, and what you do is you multiply your X value by its corresponding weight and add up, right? And that is effectively a dot product, right? It's taking this, it's the sum of weight, a W number times this X number, right? All summed up. That's a dot product. And so then what do we do with this sum? What do we do with this dot product? Well, it's some positive or negative real number, and we feed it through this threshold. And if it's positive, the neuron fires. And if it's negative, the neuron doesn't fire. And so it's testing whether the number is positive or negative, right? And what is that basically doing is we can look at the plane, right? Take the weights here. The machine has particular weights, and the weights forms a vector. And you can look at the plane that's perpendicular to that vector, and weights and input values that are on one side of the plane get a 1, get yes, and the ones that are on the other side of the plane get no, right? We get the output here tells you which side of the plane you're on, right? Does that make sense? So here's an example. Here I have two values, x1 and x2, and those values, you can think of them as 0, 1, or off and on, or no and yes, right? 0 volts, 5 volts. And if you want to take, right in here, each dot has the 4 combinations of those values. And if you want to say the and, is it true that x1 is on and x2 is on? That only occurs in the green dot, right? That's the and, while these guys are off. They don't have the and. And here these 3 have the or, right? One is on or the other is on. And here is a NOT gate where it's saying if x1 is on, then we'll be off. And if x1 is off, we'll be on, right? So those are all very interesting functions. And we can do them all by defining weights, doing a linear combination and testing which side of this line we're on, right? So what's the moral here is, well, the moral is that neurons can do AND gates and OR gates. And we can layer, what is a neural net? Is this layering of AND gates and layering of these neurons. And they can be done, they can compute AND gates and OR gates. And what does your computer do? It computes with AND gates and OR gates. So you can have a neural net do anything your laptop does, right? So if you had any concern that these were a dumb model of computation, they're as good as any computer, all right? So let's think about how well they compute versus how well it is for them to learn, right? If in each of these neurons, we we did everything linear. If everything was linear, then it's easy to know what weight should you have to compute the best as you can compute. However, the problem is linear functions aren't very powerful and you can't compute very much with them. On the other hand, if we use these thresholds like we were just talking about, right? You take the dot product and feed it through a threshold, then you get yes, no, on, off, and, or. And as we can see, they're as strong as circuits, so you can do you can compute anything computable, but it's impossible to learn. And we talked last class about feeding those dot products through something smoother, like a sigmoid function, and then it's just as powerful to compute, but it's easier to learn. And there are other weird things we could feed it through. This is called a rectilinear, and here's something else, and here's another one. These are various things that people try, and it turns out that you can all learn very well and compute very well. And all right, so now let's think about our data, each image as a point in high-dimensional space, and think about what that means. All right, so here's our training data, right? Each X value might be an image. Each Y value might be labeling of whether it's a cat or a dog. So here's an image. And what is an image? Well, for each pixel, there's a number, or maybe there are 3 numbers telling you the color of that pixel. And so it's this big tuple of numbers. And what do you do with tuples of numbers is, well, you can place them in a high-dimensional space, right? So here, this is, if you had three numbers here, then the image gets placed as a point, right? Your brightness of your first pixel is this dimension, your brightness of your second pixel, your brightness of your third pixel, right? It all places the image as a point in this space, right? Of course, you have lots of pixels, so it's a very high dimensional space, but that's okay. All right, and now we don't have one image, we have lots and lots of images, right? This could even be the set of all possible images, right? Each dot here, each point represents one of these images, right? It tells you, each point tells you the coordinate in each dimension, so it tells you the brightness of each pixel, right? And we can take all this data, right? That's a lot of data, and we're gonna stick it in a matrix because we find matrices are useful in mathematics. And what is a matrix? It just has rows and columns of numbers, and each row is going to correspond to one image, and it will tell you the pixels of all the values of all the pixels of that image, right? And what does a column do? Each column corresponds to a particular pixel, and it tells you what value how bright that pixel is in each of the images, right? So that's just rows and columns of this matrix, right? And so now we want to do, there's matrix multiplication. As soon as you have a matrix, you want to do matrix multiplication. Now, what is our goal is we want to evaluate the neural net, and we want to do it, right? What are we given? We're given all this training data, all these images, and we have the layout of our neural net, and for every edge, we know its weight, and it's going to compute. What do we want to do? Is we're going to take every image here, feed the image through this machine with these weights, and get the output, which tells us whether it's a face or not, right? And we want to do it fast, right? Why? Because we got lots of data here, and we need to do it fast. And there's these things, graphical processing units, that what do? They multiply matrices really fast and do other parallel operations really fast. And why are they so cheap to buy? Is because the video game industry, everybody who plays fast video games needs one of these things. The irony now is that they're no longer cheap my nephew Liam tells me they're expensive because people are buying them for Bitcoin mining. But anyway, suppose you're reading some paper on machine learning. It's going to write this down as a line in the text, and it will never, I find it never tells you, but you just need to know that those are not numbers, they're entire matrices, right? And you need to know that what's happening is matrix multiplication, and you should have some understanding of why we're doing that. All right. So let's see what we can do. Here's all our training data, right? And let's have an index D, which will pick out the D training data, right? When you're doing matrix multiplication, what's key is to know what all your indexes are. So we're going to start by thinking about all our indexes. Index D tells us we're talking about the D training data. And what are we going to do with that training data? We're going to feed it into the neural network. And the training data as we know, is a tuple of numbers, each one giving us the value of a pixel. And so we can talk about the ith pixel, right? Here's index I, can talk about the ith pixel. And where does it go? We feed that number into the ith node at the bottom of the neural net, right? So we have our D training data, the ith pixel, and we can talk about XDI is then going to be how bright is the ith pixel of the D training data, and that value is going to get put in right there, right? So let's now talk about hidden nodes. At the next layer here, for each J, index J, there's going to be the Jth hidden node at this layer, and we're going to index it by J. And here we have an iceberg that's mostly hidden, so that's why I'm using it for our hidden nodes. And these hidden nodes, I said last time, have no real meaning that is human designed, but we can define these Y values, which is does the Jth hidden node on the D training data, is it firing, right? Some number between 0 and 1, whether it's firing, right? We feed in the D training data, we look at the Jth hidden node, how much is it activated? All right, that's great. And then there's this pre-activation level, right? What is it? It was, I changed the slide this morning, but I guess it didn't copy over. Hello? All right. So the pre-activation level, remember, is the sum of the dot product, right, that you feed into the sigmoid function. So anyway, we can also calculate for every hidden node the Z value. All right, and now there are all these edges, right? For every node I and for every node J, there will be an edge between them, and they have some weight. Wij is the weight between them, right? And so these are the numbers that we need to compute. And how are we going to compute them, right? We're going to take this activation there, and each X number here gets multiplied by its weight, and that contributes to the Z, right? But of course, there are many nodes coming in, right? Each I has its own node. So we're going to sum them all up and get this equation here, right? Remember, this is just the dot product here. We sum over all the i's of the X value times the weight gives us our Z value, what we've been doing before, right? And here it is written out if you don't remember that that's the sum thing, right? It's just the sum. All right, so I've told you already that this is kind of a dot product. Here's a vector, and here's a vector of numbers. And when you take a dot product, is you multiply like that. You take this number times this number times this number. You're going around like this, and then you add them all up. and you put that sum over here. All right. And here it's what we're summing through is this index I, right? So that's, and let's put our other indices, right? Here, this value is for the dth training data and the jth hidden node, right? And those are all our indices. All right, well, that's good. But now it's not just this one hidden node that we want to compute, right? We have many hidden nodes that we want to compute. And we like to do things in parallel. So we compute them all in parallel, right? And then we're putting in this dth training data, but really there's many training data and we want to compute them all in parallel, right? So we do them all in parallel. And what you get here is these matrices. Let's review what these matrices are, right? This matrix for every I and j tells you the weight between I and j, right? This is the matrix we looked before, which says for each training data in each pixel, how bright it is. And this is our new matrix, which is for each training data, how is the jth activated? And this is just matrix multiplication. If you remember from high school, how do you compute this value of matrix multiplication? Well, you look at the same row and the same column, this column, and you do a dot product, and that gives you that value, and that is matrix multiplication. All right. So we can have this matrix times this matrix gives me that matrix. All right. So let's try to think of different abstract representations of the same data, right? We're going to start with an image, right, which tells us the pixel values of all the, right, how bright each pixel is. And we're going to feed it into this neural net, and we're going to see what it does to it as what happens to all these numbers as we go through. And just as a reminder, each of these dots corresponds to one of the pixels. Well, here, this single dot represents the whole vector, right? So this single dot corresponds to all of those dots, right? Just to make sure we don't confuse our dots. They're different sorts of dots, right? So what are we going to do with this data? It's going to, our neural net is going to transform them to get new numbers, right? And what are these new numbers? Well, we can put these new numbers as, right, this first number could be this first coordinate, and the second number could be the second dimension, and the third number could be the third dimension. So that places this, all this is a vector, which places us somewhere else in this new vector space, right? And then we go over again, and it keeps transforming this image until suddenly it can say that it's a face, right? And so let's do that again. That was fun. But instead of one training data, one image, we have lots of images, right? So those are all our images. And we're only going to feed one of them through here at a time, right? One image is going to come at a time. But here we're going to, in parallel, going to see what this machine does to each of these images, right? So here's another picture, right? We just having it in 2 dimensions. And remember, the red dots might say it's a face, while the blue dot might say that it's the bicycle. And so here, this particular, this tuple of values here will be one of these dots. And we feed it into the neural net, and it does some transformation on it, right? Then we feed it into the next layer, and it does some transformation, right? Each layer does some transformation until suddenly we have it so that we can do a test to see, oh, is it a red circle? Is it a face, or is it a bicycle, right? And I think it's kind of fun to see, you know, what these transformations might be doing to your data. All right. So first off, let's think about an image. it has lots and lots of pixels. This is a random image, right? And so there are lots and lots of these images, lots of random images. And so the set of all possible images is a really high dimensional space, right? It's a crazy thing. But the belief is that the images we care about, they all lie in some nice connected space, right? Why is that? Well, here, these are all images that we care about. And maybe this first image it corresponds to that first dot, and the second image corresponds to that second dot. And you see, as we go from one image to the other, the image isn't changing very much. So it's not moving far in this space. And we have, that sort of argues why the images we care about fall in some sort of space. And if we can transform that space in some way, then we might be able to learn that what kind of, whether it's a bicycle or a face, right? So it's good to know what multiplying by a matrix does to your data, all right? So you might remember that matrices can rotate your vector space and in various ways. And so it can do all of that. It can also stretch it in various ways. And since we are adding on this extra weight here, it can also shift it left and right in various ways. And so also here in this case, look at, I have more hidden nodes than I have input nodes. So that's increasing the number of dimensions, right? And so what does that do? We have our data placed in a low dimensional space, and we're kind of shifting it into a high dimensional space, right? And why would we want to do that? Well, having our higher dimension space gives us more freedom to move things around. The negative is that you have more data, so the computation's more expensive. Having more powerful machine can lead to overfitting. Remember, overfitting was when your machine does well on the training data, but doesn't do well in the test data. Anyway, that's another option. Is here I'm putting the lots of pixels into a few hidden nodes, right? I decrease the number of hidden nodes. And what's that doing? That's effectively taking our data and we projecting it onto some lower dimensional space, right? That's a two-dimensional example. Here's a three-dimensional example. Here's a three-dimensional image that we project down to 2 dimensions, right? And why might we do that? Well, these faces are all described by 10,000 numbers, right? That's a lot of numbers to be working out. And if you can do a projection down onto only 100 numbers, where you can filter out what are the important features of, right, which 100 numbers, right, or you get 100 new numbers, which somehow represent these 10,000 numbers. And it's then easier to recognize whether this is a face or a bicycle. All right. So here I'm just saying, what's important about this picture? Well, it's a person who's not very happy, right? We extract out the important details.
It's called data abstraction, if I'm not.
Exactly.
Yeah.
So now what happens if you do one matrix multiplication and then you do another matrix multiplication? What's that happens? Well, it turns out that you can put the brackets in different orders, and it boils down to doing just one matrix multiplication. And so that means there's no reason you would do 2 matrix multiplications in a row, right? And so we have to do something nonlinear in between. And what we're doing is just this sigmoid function, remember? So here we have all our Z values, a matrix of the Z values that we've computed. What are we going to do with them? Well, for each, we're going to apply the sigmoid to each operation, right, in parallel. Apply sigmoid to each of them, and it gives us our Y vector, right? Here we're going from this X value to this Y value, right? And what does that do to us here? It says Big positive numbers go to 1, big negative numbers go to 0, right? And so if you have all these data points and everything gets moved closer to 0 or 1, it kind of moves everybody to be kind of like that, for whatever that's worth. And a rectilinear one is rectifier, lets electricity go forward, but doesn't let it go backwards. And it kind of moves all negative numbers to being 0. That's kind of what it does. And so it's hard to believe that these weird combinations are useful, right? But we take our input data, right? And it somehow works. All right, so now let's go back to how do we actually compute the output, right? We take our input values that we fed in there, and for each of the layers, right, we're going to compute, right? So we take the X values, we do the matrix multiplication to give us our Z values. We take our Z values and feed them through sigmoids to get us Y values. And then our old outputs will equal our new inputs, right? And then we loop and we do it again, right? We do it again, we do it again, we do it again. And then in the end, what do we want with these numbers? Well, we want them we're going to pretend that they're probabilities, even though there's no distribution. So we want each of them to be between 0 and 1, and we want them to add up to 1. So we're going to take our Z values and pass them through this funny function, which is going to give us our output. We have too much to talk about today, so I cut this out. But I suppose if we have time at the end, we could understand how this function works. All right. All right, actually, we're doing pretty well for time. I might be talking too fast. So let's talk about gradient. How are you doing, Shanaz? Are you following this?
Yes, sir. This is very interesting, actually.
Excellent, excellent. All right, so let's do gradient descent. All right. So remember how it works. A robot wants to learn how to take in an image and recognize if it's a face or a bicycle, right? And what it uses is it needs to learn these weights, right? What it does is dictated completely by these weights. And we can think of our current, we're going to keep changing our weights. So let's think about, as we learn, we change the weight slowly. So let's think about our current weights can be thought of as a location in weight space. So what does that mean? If we only had 2 weights, then they could give us our longitude and latitude. And then what we do with these current weights, we have our current location, which gives us our current weights. We have our current weights. We feed all our training data through it, which gives us all our answers. And the supervisor then says how much error there is. And we have the height be what the error is, right? And then the supervisor helps us choose a direction, and the machine moves a little bit in that direction. And what that effectively does is it changes all the weights slightly. So we have new weights now, right? And if we were to do that calculation for each setting of the weights, then we would know the error for every setting of the weights, and we would have this error surface, right? And what do we want to do is we want to start in a random place, and we want to keep traveling in the direction of steepest descent until we get to a bottom of the valley. That's the algorithm. Just keep going down. In fact, pretend you're water, and what direction is steepest down is the way water flows. So you dump a bucket of water and you watch how it flows down the hill until it gets to the ocean, right? All right, so let's try to visualize that a little bit more with vector algebra, because I know you all want to learn a little vector algebra. So here is our surface, and another way of representing a surface is by contour lines. You've probably all seen this on a map. So here's our 3-dimensional hill. and you draw a line at every height, and you project that down onto your map. And so then you get these contour lines, right? And we have a current setting of all our weights, which of course tells us where we are on this map. And if we were to move following that contour line, there is moving following the contour line, we will get all various locations at exactly the same height, right? Exactly the same error, right? And we want to go in the direction of steepest down, descent, right? But we can calculate steepest up. The steepest up down is going to be perpendicular to that contour line. All right, we'll talk about that later. So there's the direction of steepest ascent. Steepest up is in that direction. We're going to later calculate it. It's some ugly calculation. We'll talk about later how to calculate that direction. And what do we do with that direction? It's also a vector, right? We're going to negate it because why? Because we don't want to go up. We want to go down. We want to descend. And then we're going to take a step size, some little number, because we don't want to go too far, right? If you go too far, you're going to go down and then you're going to start coming back up again, right? So we don't want to do that. So we multiply it by some little value. So we take a little step and then we do vector algebra. And what does that mean? Is that this light green dot can be thought of as a vector from the origin, is where we are currently located. And this is the vector of how we're changing. So we add this vector to this vector, which gives us this vector, which is our new weights, right? So that's that's adding vectors. If you don't like vectors, but you want to deal with, right, each vector is a tuple of numbers, has all these dimensions, so it has all these indexes. So you loop through all of these indexes and you just add the values one index at a time, right? Is that kind of making sense? All right. So now it comes
Jeff?
back to which direction is steepest up, steepest ascent. And people say, well, of course, that's the direction of steepest ascent. And I've been doing math for a long time, and it was never obvious to me that this was the direction. And so I've thought about it a number of different ways, and let's try to explain. We're going to explain two things: how do we compute all these numbers, and why those numbers will give us the direction of steepest ascent. All right. All right. So as I say, we want to calculate all these numbers, and we want to understand what all these numbers mean. And so let's talk about how we're gonna compute them, or how one could compute them. It's not how we're going to compute them, right? So we have some current location, right, given by all our current weights. It gives us a point on the map, and we do forward propagation. We propagate through the neural net all our training data, and we calculate what is our error, what is our height at our current location, right? And then we're going to need to compute this value for every weight k. So for each k, for each weight k, we're going to do the following. What are we going to do? Is we need to compute this value, this derivative, right? This is calculus, it's a derivative. So how do we compute it? Well, we make a small change. So delta W is an infinitesimal change. We change this one weight by an infinitesimal amount. We don't change any of the other weights. And then we recompute the error, right? We feed everything through the machine, and this tells us what is our error. Note, I've changed weight k to be slightly bigger, right? And that's going to change the error. And then we're going to say, well, how much did the error change? Did it get better? Did it get worse? Right? we're going to take the change in air, which is the new air minus the old air, and we're going to take the ratio of how much did the air change divided by how much did we change that particular weight, right? It's a ratio, it's a slope, right? Rise over run. And that's going to somehow tell me how this weight influences the air, right? If I increase this weight and it increases the air, then you're going in the wrong direction, right? Then you want to decrease this weight so that it decreases the air, right? Does that make sense? Now, that's the intuition of what we're doing. But of course, that would take way too much computation time. We can't do that, right? So instead, we're going to do what's called back propagation. And we're going to propagate back and we're going to compute all of these derivatives. And we're going to do it just exactly like you did it in high school. There's really nothing here that you couldn't have done coming out of high school. All right. So here's a picture of calculus. And let's see if we can do it. All right. So let's imagine a staircase and you're looking down on it from above. So our east-west, our east-north direction, our location is giving us what? It's giving us our weight 1 value and our weight 2 value, right? It's giving us our various weights of our machine. And then the height, as you go up the stairs, what's the height telling us? It tells us the air, right? So for example, if I'm at this purple dot, then my W1 value is 5 and my W2 value is 3. And I have some height because I'm on some stair. And that tells me the error, right? If I took these weights and I fed all the training data through it, then I would get this amount of error, right? Does that make sense? And what is our question? Our goal is to find the direction of steepest ascent. And I think all of you know that that direction is not the direction of steepest ascent, right? Why? Because if we'd gone straighter, we would have gone further. All right, so let's make our stairs look a little bit more abstract. These are our contour lines. And if you travel in this, if you travel past the contour line, then it raises us up by a foot, right? So as I remember our algorithm, what we did is we took weight 1 and we changed it by 1. So we changed it from 5 to 6. The change in weight is 1. Of course, I said we would do infinitesimals, but let's make this more concrete. And what does that change in our height? If you count the number of contour lines we go over, we went up by 4. All right. So we changed the weight by 1. The height changed by 4. Rise over run, that gives us a slope of 4. Right. Every time you change the weight by 1, it changes the height by 4. All right. Then we can do it in the other direction. Right. We change W2 by 1. And so that's a change of 1. And this time, look at it changes the air by not by 4 anymore. This time it changed the air by 7. Right. So this time you change the weight by 1 and the air goes up by 7. So the slope, rise over run. I really got to figure out how to tell it not to do this. It didn't used to do that. It just started doing it this morning. All right. So rise over run, right? We have 7 divided by 1 is our slope, right? All right. Now we want to know, can we put this over somewhere else? Let's see. How do we take this? I don't know how to get rid of it. See, I get email from so many people. Anyway, there it went away. All right, sorry. So now we want to figure out which direction to head to get steepest ascent, the steepest slope. And you can imagine putting a book on your head and you slope it forward by 4. You slope it sideways by 7. and then you put a marble or water on it, and you see which direction it moves, right? That would be the which way it rolls. That's this direction of steepest slope. Another way to think about it is from your location, you step a distance of 1 in every direction, right? So this purple circle is where you can get to in one circle, in one a movement of 1. And we want to know where in that circle is it the highest. And it's clearly that spot right there. See, it's the contour line perpendicular to our circle. And you should be able to convince yourself that that direction is perpendicular to the contour line, right? So that's now what we're trying to try to do, is find the direction that's perpendicular to the contour line. All right. So here's the purple direction that we're trying to find. And if you look here, we have a triangle in here. So let's emphasize this triangle. It's some triangle. All right, so now these aren't the same change in W's we had before. This is a different change in W. We're gonna choose some contour line out here that we like. And this change in W1 is how much we have to change in W1 in order to get to that contour line, right? And similarly, this change in W2 is how far do we have to change W2 to get to the same contour line, right? So these are two numbers. And the advantage of those two numbers is we can flip the triangle, right? This is the same triangle flipped around, similar triangles. So we can put the short distance was our W2 and the long distance is our W1. And then since it's a triangle, we can scale it we can multiply it through by any constant we like. So we're going to multiply it through by this funny constant. All you have to know is it's the same. And things cancel, right? This cancels with that, and this cancels with that. And what do you get? You get that this direction is this number. And what's this number? It's the rate of change of the air as you change W1. And what's this one? It's, right, as you change W2, how much does it change the air, right? These were our derivatives that we were claiming that were so interesting that we computed. And what were those numbers, right? They were 4 and 7. So this vector here is 4 in this direction and 7 in this direction, all right? And amusingly enough, you might then ask, well, what's the slope in this direction, right? The slope in this direction is 4, which is the length of this line. And the slope in this direction is 7, which is the length of this line. And the length of this line, if you do the Pythagoras theorem, is 8. And you'll note 8 is bigger than both 4 and 7. And that is the slope in this direction. All right. So we had a slope in one direction, a slope in the other direction. And the best slope is bigger than both of those. All right. Does that make sense? All right. So now we're going to do back propagation. All right. What is our goal? Our goal is to compute all of these derivatives. And some of you probably are losing, some of them are following. But anyway, let's see if we can compute all of these derivatives. And we're going to do it by calculus. All right. So first off, there are a lot of these derivatives to compute. And you could start at the beginning and move through your neural net computing all of these derivatives. And right, so for each of the lines here, we would need to know what's the rate. If you change this, how does it change that? If you change this, how does it change that? There's a lot of derivatives to calculate. In math terms, let's say it's quadratic number of derivatives, right? It's n times n squared derivatives. That's too expensive, right? So instead, we're going to come backwards. We're going to do, why do we do back propagation? It's because there's only one output, right? And so for each number here, we can calculate if we change this slightly, how does it affect the error? If we change this slightly, how does it affect the error? And now there are fewer derivatives that we have to take. All right. All right. So let's think again how we're doing it. We have our current weights, right? Current weights on our machine. What we do is we take all our training data and we feed it through this machine, forward propagation to give us all the outputs to give us our error, right? And then we need to compute all these derivatives, right? And how do we do that? Is we take the derivative here, we back propagate derivative here, these derivatives, these derivatives, these derivatives backwards, all right? And the way you do it is just chain rule, all right? So and it's all going to boil down to matrix multiplication again. And in order to do matrix multiplication, we need to know all our indexes. So let's have a review of our indexes, all right? The first index D tells us which training data we're working on. Index I will tell us a hidden node at this layer, the ith hidden node at this layer. And for each D and I, the X value can tell us how, right, what's the firing of the ith hidden node when you're feeding in the D training data, right? You feed in the D training data, you check out whether the ith node here is firing. That's telling you, that's told to you by this variable, right? Similarly, we can go up to J, to the next layer. We can talk about the jth node at this layer, and we can talk about Y is how much it's firing on the D training data, right? And let's back up a bit. Remember here, the Y value is whether the neuron's firing, but we want something slightly earlier. Let's back up and get the pre-activation value, the Z value, all right? So instead, we're going to talk about Z here is the D training data, the ith node here, what's that pre-activation number, right? And then for every I here and for every J here, there's an edge, and that edge will have some weight, Wij, right? And so these are all the numbers. These are all the numbers that we need, right? And where did we get all these numbers? Well, when we did forward propagation, we stored all these numbers in some big database, matrices, lots of matrices, right? And we remembered them all. All right, now we need to do what we need to remind ourselves what our goal is, right? Our goal is we're going to change that weight by a little bit, right? And that is going to induce a change in the final error, right? You change that weight, that change propagates through here, it changes the final error. And what we want to compute is this ratio, right? If we want to compute what's the change in the error divided by how much we change the weight, right? All right, that's what we want to compute. What's our next sort of value coming along here? There's this Z is the next value coming along. So let's bring it in. What we're saying is you change the weight, that changes the Z value, and that Z value in turn changes the error, right? So there's just a path of change. All right. All right, now this derivative with respect to the Z value, suppose we computed it already somehow, all right? We did back propagation, we computed that value. What are we going to do with it? Well, we want to compute this value from that value, and the way you do it is chain rule, all right? And what does that mean? That just means you make sure everything balances, all right? Here we have a change in error on the top, change in error on the top. So that balances, right? But these things on the bottom, they don't balance, right? So to make them balance, we bring in these numbers, and you'll now see that the blue guys cancel, and what you get is the orange divided by the green, and you get what we want. All right, so that's chain rule. And just to review what we got here, right? We're looking at, you change the weight a little bit, the W a little bit, that changes the Z a little bit, and that changes the air a little bit. And we want to know how those changes relate to each other. That's what this equation says, right? It's how does the Z change when you change the W? How much does the air change when you change the Z? How much does the air change when you change the W, right? That's what we're looking at. But it's more complicated than this. The problem is, if you looked at this equation, on this side, we have the index D, and on this side, there is no D, right? So we got to figure out what these D's are doing. And remember what the D's are doing, it's our various training data, right? We have a lot of training data. And remember, the air is some fancy combination of all this training data, right? In fact, it's a sum. The air is a sum of the air for each of the training data, right? So really what happens is when you change the weight, it doesn't change just the one, right? This Z is the firing, the activation of this node on the D training data, right? But we have all these Zs. We have how does it react on the first training data and on the second training data, on all our training data, right? And each of those in turn influences the error, which so and it's accumulative, right? You have change here and change there. And so this, remember, this symbol here means add this up for all values of D. All right. All right, that's our equation that we need to compute. And before we can compute it, I told you we had this already and we want this already. So what we need is we need this number, right? And so let's think about how we can compute this number. All right, let's go back to our artificial neuron and remember how it works. It has X values coming in, and each X value is multiplied by a W value. And that gives you, this weighted sum gives you a Z value, right? So Z is this sum, right? It's you multiply here and you add it up. So that's our value of Z. And we can ask the question, why did I circle this one, right? Because this is the weight we're talking about. This is the weight in question, right? And if I change this number here by 1, right? Just increase this number by 1, right? See what effect does it have on Z, right? Well, it's going to, that 1 is multiplied by this X. So it's going to change Z by this X value, right? And we write that down as the rise over run. If you change the weight by 1, it's going to change the Z by X, right? The rate of change of Z with respect to W is X. All right, so that's our number. We can plug it into where we need it, right? All right, so this is our equation that we need to compute. And remember, we can do it for all J's in parallel and for all I's in parallel, right? This is a particular IJ. We can do them all in parallel. And it all boils down to, how do you compute this number? Well, you take the dot product of this row and this column, which is this equation, and you have matrix multiplication, right? All right, so that was fun. So let's do it some more. Let's do it one more time for good luck, right? Remember, I told you that somehow we computed all of these values using backpropagation. So now I have to tell you how to compute these values. All right, so let's start back here. We're kind of in the middle somewhere. And I'm going to change this X value, which is, it's not going to change the weight. The weight doesn't change, but I change this X value it changes this this y value, and the y value then in turn changes the error, right? So here's a path of change. You change this, it changes that, it changes that. And let's assume by induction backwards, right? We're going backwards. Let's assume that we've already computed these derivatives, right? And what we want to compute is this derivative. So this is what we want, right? We want to, given this, we want to compute that. And again, we use the chain rule, right? So we say, hey, look at the change in error is on the top, but we don't like what's on the bottom, doesn't match up. So we multiply by this to get rid of the thing on the bottom, but then we multiply by this to get rid of the thing on the bottom. And then look at, we have everything balances out, right? So that's our equation. And what is it telling us? Tells us if you change the x, it changes the z, which in the change the z, it changes the y. You change the y, it changes the error, right? And that tells us how changing the x changes the error. All right. Now we have the same problem we had before, but not with the d, it's with the j. Look at, we have an index j here, but we don't have an index j there, and that's a problem. And why is it? The reason it is because when you change this x value here, it doesn't change just one of the y for one j, it changes the y for all of these j's, right? All of these y's change, and each of those in turn changes the error in the end, right? So to handle that, we sum up overall values of j, because everything here is linear, right? And that's our equation that we have to compute, right? And so we know we have this one, we want this one, but we're going to need this one and this one. All right, so let's start with this one here. What is it asking for? It's asking, if I change my x value a little bit, how much does it change my z value? Remember, the x value feeds into this neuron, which gives me a z value, right? Which later gives me a y value, right? But first, how does it change the z value, right? Well, how do we compute it? You've seen this exact sum before, right? You take each x multiplied by a w and add it up. So the term in question is this one. And if we change the x by 1, that 1 is getting multiplied by this w. And so z is going to change by w, right? So the rate of change of z with respect to x is going to be this w, right? If you all remember calculus. And so we can plug that value out. And one of the things that's cool about this, I was trying to work this out myself, is look at this, has a d, j, and an I in it. We don't like d, j's, and i's. That's way too many indexes for matrix multiplication. But when we do this, it only has an I and a j, and that makes me happier. All right. All right, so now let's compute this one. What's this one's doing is I change my z a bit. How much does it change my y? And how do we do that? We take the z and we feed it into the sigmoid function, right? There's our sigmoid function. Remember, what it does is it takes positive numbers and turns them into things close to 1, takes negative numbers, turns them into things close to 0, right? And we now need to know what is the slope of this curve. We need to differentiate this curve. How does y change with z? Well, we're going to do proof by picture. Proof by picture says, when is the slope almost 0, right? Up here, it's almost 0. Down here, it's almost 0. Well, when is that? Well, up here is when y is close to 1. And down here is when y is close to 0. So we need an equation that's 0 in both of these cases. And it turns out to be this, Why is that, right? Because if y is 0, you get 0. If y is 1, you get 0. It's a nice equation, and you can believe me, it's the answer. Though you could do the math yourself if you needed to, right? So that's the derivative there. And let's go back to where we are, right? We need to compute this thing. Well, let's put brackets around that. Why am I doing that? Because everything in here has a d and a j in it, right? Well, this has an ij and this has a di. And we write it down like this, and you'll see what we get is matrix multiplication again, right? How do I, this is here's a matrix of values. For every d and every I have to compute this. So I can form a big matrix for every d and every I can say this is what I want to compute, right? And similarly, we get a matrix of these indexed by d and j. And here, this is the matrix of weights indexed by j and I. And you do the matrix multiplication and it all works out, right? Does that make sense? And once I tried it in a spreadsheet, and it was way too weird. I'm going to say one last thing here. I find this lots of fun. All right, all of this, what we just did there, can be automated. How so? Well, suppose you design this machine down here with these connections and these weights. You definitely, given the inputs x and the weights on the machine, you have to write a program which will compute the outputs of your machine, right? And given the outputs of the machine, you need to write a program that will compute the errors, right? So basically, you've written code which takes in the inputs x's and the weights w and gives outputs the error, right? And so what we're needing to do is we're needing to differentiate what is the derivative of E with respect to each of these weights. And somebody wrote a program, a compiling program, just like your compiler. It takes this code as input, it outputs new code. And what does the new code do? Is it computes all these derivatives for you. When I heard about this, I said, what happens if you asked it to sort, to compile sorting? And he gave me an answer that convinced me. And that's the end of this talk. And look at, we did it in pretty much perfect timing. Maybe it was too fast, but we got through it. Should we open it up to questions? I'm curious how many people are still with us and how many people just got lost. I know lost. Jake got lost, but yeah. Sorry, Jake, you don't really count.
Thank you so much for the talk, Jeff. I do see a couple of questions in the chat box. So,
all right. Here, let me bring down the chat. We got to thank you. Verify with Jeff that. Oh, let's see it. Scroll up.
Yeah. So let me just get it from the scroll up. Then you don't have to do the work. Dinu was asking if you could recap on the ReLU function one more time.
The what function?
I'm pronouncing it wrong. ReLU, R-E-L-U.
Hey Jeff, hi, Dinu here.
Yeah.
Thanks, Dinu.
So
the
in the beginning.
Right. That is here. That's the regression. You know, I don't know much more than the picture says. Right. What is it's all proof by picture here. We where would it be? It would be under right about here, I think. So this is right. This is a sigma, right? Let's see a threshold, right? A threshold takes positive numbers and returns 1, takes negative numbers and returns 0.
Yes.
Right. A sigmoid does that a little more smoother, right? This is graceful, right? This function, what does it do? If you give it a positive number, it doesn't change it at all, right? If your electricity is moving forward, it doesn't change it. But if your electricity is trying to go backwards, right? It's a rectilinear, a rectifier. It keeps the electricity going backwards. And so it turns negative numbers into zero. And that's what it does.
Oh, I
And
see.
then you ask, well, why are we doing it? And the answer is, why do we do any of this stuff? Some grad student probably wrote his PhD on this. He said, what happens if I try to learn with these instead? And it turns out it learns better. Now, what's the intuition? The intuition here is when the derivative is almost zero, then remember how we're calculating, you're not, you know, the water, if you put water here, it's not flowing very fast because it's not very, it's almost flat. And so not much learning happens up here, right? And the advantage of this is the derivative here is 1 everywhere. Oh, here the derivative is 0, right? So that's no good. And so then we can kind of talk about other functions, right? Where are my other functions? Here we go. Right here, right? You could just try various functions for whatever it's worth. Here, the problem is the derivative's always 0. That's not good. So you're not making any progress. So we change it here. Now you have some derivative everywhere. And here's another weird function. Why would you ever have that be a function? I have absolutely no idea.
Okay. Yeah, I think now I got clear. Sure.
Right? All right, next question.
Hi, Jeff, it's Shanaz. That was very interesting. Thank you. Some of the stuff I think I would have to take a few more courses to understand, but it's okay. Going back from the last few slides, you changed one of the equation. You changed it to the weight, Wi, comma J. Why did you do that? Like, was that necessary to do that? You said you want to make it look simple. You know, if you go back from the
Do you have any idea of where we are?
Yeah, right. One of the last few slides.
Last few slides.
Yeah, so I wish I had written down the slide number. You know, yeah, this one. No, go forward. Yeah. You see that? Now you change that and then you kept going and then you said, okay, well, I'm going to change so keep going, and you changed it to the last ratio, you changed it to Wij. You said this one right here. So what was the purpose of doing that, changing the last multiplication to the weights instead of?
Oh, well, because we have this equation here, but we need to compute all of these values before I want to compute this value. And I assume I have this value by induction. And now I need to know these two values, right? This says how, right? This says, how do I, if I change X, how does it change the air, right? Well, this says, if I change X, how does I change Z? If I change Z, how does it change Y, right? And then when I change Y, how does it change the air, right? So I computed these values in the past. Now I need to compute this value and this value. So we compute them, right? This says, if I change this X value by 1, that 1 gets multiplied by this W, and the Z goes up by W, right? And that you might remember from calculus, what's the derivative of Z with respect to X, right? Well, all these terms are constant, right? Because I change this X, all these other, nothing else is changing. Just this X is changing. So all of this drops away. And now what's the derivative of this with respect to X? Well, W is not changing, right? So W is a constant, like 5. What's the derivative of 5X? Is 5, right? So that's what we're saying here is, what's the derivative of 5 times X? The derivative is 5, right? And that gives us this value.
Yeah, that makes sense now. Okay, thanks.
Right?
Yeah.
And similarly, we do the same. If we change the z by a little bit, it's going through the sigmoid, right? So we need to know the slope of the sigmoid, right? What's the rate of change? This is saying, what's the rate of change of y when I change z a little bit? That's the slope of this curve, right? Does that make sense?
Yeah, that's a little too much, but yeah, I got the other
Right.
part. Yeah,
Well,
I got the
we
derivative
can,
part.
you know, we can review calculus more. We should do some calculus.
Okay.
Any
Well,
other
thank you.
thoughts?
Yeah. Thanks.
I think Reza have a question. Reza, do you want to unmute yourself and ask the question?
Thank you very much. Thank you so much, Jeff, for the excellent presentation. I appreciate it. I just read something and it was very aligned with what you said, but I couldn't, figure out one part of it. If you please just go to one of the slides that it has the neural net, like the last one, it could be.
Like,
Well,
is this?
105 has 105, I guess, has, yes, exactly. That's the one. 105.
105 is this one. Good.
Yes. So the thing is, at the beginning, we know weights are going to get initialized randomly, right?
Right.
So we just, have those things, and for instance, we want to classify if it is cat, if it is dog, it goes false. So we say, okay, now is the time to just change a little bit and do some modifications. So the ideal form could be, just we imagine that the one which is very close to cat, the label that we have, right? So we're going to say, okay, let's freeze the rest of the weights that we have. Let's just tweak a little bit towards bigger or towards a smaller number, and then we see if it goes better to a better prediction or worse. But because we need to do that for all of them, it's kind of impossible. That is why that's the point that I start my question. That is why that instead of freezing the rest and just working on one, we do the derivatives. And we hope that the example that you said about the book, that if it is going towards this side or that side, so we can tweak it for all the others. What I cannot understand, still we have something that's relevant to the rest of them. So we just, decrease the number of complexity just one level, because still, if you change it to any direction, it's going to impact the rest of the n-1 other levels. So how can it help us?
I think that there's a mistake in what you said. You said what we do is we change each weight one at a time without changing the others. And then you said that that's impossible. No, it's not. That's exactly what we do, right? Really what we're doing is we compute given our current weights, we compute the error. And then for each weight, we change that one weight by a little bit. We keep everybody else exactly the same, and we see how the error changes, right? And then we take the change in error divided by the change in weight, right? So that's conceptually what we are doing.
I see.
Right? Now we do it in parallel efficiently by all these matrix multiplications, right? But in the end, what we really get is there's a book on your head and you could change all the weights and it would be confusing. So we change one weight forward, what's the slope? Change one weight, the other weight, what's the slope? Right? So we really are looking at the slope in each direction. And then once we have the slope in for each perpendicular direction, then we use that vector of slopes to give us the direction of steepest descent.
Sure.
And I've had various people, like my son even say, well, obviously the direction of steepest descent is this vector where you compute the derivative in each direction. And I'm like, obvious? Man, that was never obvious to me, right? I mean, why should I slope this direction a little bit? I slope this direction a little bit. Now, which direction does the marble roll? Right?
True.
It turns out to work, but I wouldn't call it obvious.
I see. Yeah, thank you so much.
Right?
I
Does
do
that make
appreciate it.
sense?
Yeah, sure, totally. Thank you so
I think
much.
it's obvious.
Hey, excellent, Jake. Let me give Jake some credit. He and I were talking about this stuff, and we got up to -1 times -1 is +1. And that's why I have it in the slides a couple of times, because it's important to know. Any other questions?
Well, I have lots of questions, but I didn't even know how to ask them.
All right.
I don't see any new questions on the
All
chat
right.
either, Jeff. So
All
yeah,
right. And we've
thank you
run
so
out of
much.
time. All right. Well, thanks, everybody. I hope you get all your friends to come. The next talk is going to be about we get the right answers for our training data, and why should it at all do well on data we've never seen before. If people haven't noticed this, every time for every talk, you need to register again. And I found it personally hard to find where to register. So I had some, when I had slave labor, I had some student find it for me. And I put the links to some of them in this link. This is my link page. You just go to my homepage and you go to machine learning. And at the top of it, I have the registration page for the next couple talks.
Comp sci.
And otherwise, we'll see you all next week or sooner.
Okay.
Thanks for coming.
Thank you.
Thanks, Jeff.
Thanks a lot, everybody.
Jeff Edmonds, comp sci.
Okay. Bye,
Bye-bye.
everybody. I'm going to push.
Yeah.
Bye.
Going.
Bye, Jake.
Bye. Thanks.